This is the 47th lecture in a course on single agent search. And in this lecture, we're going to be looking at abstraction and refinement techniques. These are techniques that have been used a variety of different times in the past and actually have quite a long history in the literature. And even when we go back to like Valtorta's theorem, when Rob Holte was doing work around Valtorta's theorem, he was looking at abstraction and refinement techniques at that point in time. However, they have generally fallen out of popularity except for in one domain where they still are very popular, which is in the domain of video games. So we're going to look at abstraction and refinement. And you still see there's quite a few games that are using these sorts of techniques today, and even more games in development. And so I'm going to give an overview of the ideas today, and we'll look at them here, and then we'll talk a little bit about why they work, some of the properties around them. And then once we have that, we'll take a look at a demo of how it works in practice. I'm also going to talk about some of the techniques that allow this to work well in practice that have actually been used. So this is a technique that I implemented in the game Dragon Age Origins, and so I'll be able to tell you a little bit more about that. And actually what I can show you here to start out is back when we looked at the idea of abstraction. When we were looking at the idea of abstraction, we were talking about how abstraction doesn't work particularly well in grid maps or some types of abstraction. And so this is actually an example that I built some time ago. I didn't have it in that lecture, but this is showing a portion of a map. And on the left-hand side, you can see the original representation of the grid, which is in green. And on the right-hand side, you can see an abstraction of the map, and we'll talk about what this abstraction is and where it comes from. But this is an abstraction that reduces the number of states by about a factor of 4. And you can see that the heuristic value, this is a two-dimensional map, so the square root of 4 is 2. And we've reduced the width of the map, that is the maximum sort of diameter, from 157 to 80. And so trying to get a heuristic out of this abstract state space that we can build here is not going to be very appropriate. Although if we wanted an inadmissible heuristic, then we could multiply it by a factor of 2 and get a potentially inadmissible heuristic coming from it. But anyway, we have this state space. So basically we can abstract the state space away and get a smaller state space. And what we'd like to do is understand how do we actually do that in practice, and what are some of the trade-offs of doing that, and some other things related to that. So we're going to use an example here on the right-hand side. And we're going to look at a few different properties. And in particular, I'll come back to this, but we're going to be looking at the idea of downward refinement. And another idea that's important is serializable sub goals. Okay, so downward refinement basically says that I can take a path. If a path exists in my abstract space, it's also going to exist in my low-level state space. And serializable subgoals says that once I achieve one subgoal, that I'm able to forget what I've done before and continue to achieving the rest of a subgoal. And so we'll come back to these. And there's an interesting question that I'll defer, but here there's a question is, do PDBs, pattern databases, have these properties? Okay, and so that's something to think about as we're going through the lecture here. But the idea here is that we're going to take our state space. So we're going to be looking at this map over here. This is our state space, and we're going to think about, for this state space, how I can represent this in a more abstract way. And so I've actually given some hints here because I've put a grid on my background here. And the way we're going to do this is we're basically going to group states that are strongly connected. So there's some background here, but our basic idea here is we want to group strongly connected components. And in an undirected graph, this is fairly easy. It's in a directed graph, this is quite a bit more difficult to do. But if we can group together our strongly connected components, and then when we've grouped them together, we want to add edges between the groups. If they're reachable. And let's use this map over here to see how this works in practice. So what I'm going to do here is we're going to, for efficiency purposes, we're going to use grids for this purpose, because grids allow us to do this efficiently for the idea of, for instance, looking up states. And so what we're going to do is draw an overlay here with some grid cells, and I'll draw a couple, and then I'll do the rest behind the scenes. But what we're going to do is, basically what we're going to do is we're going to draw a line across here, and we're going to draw a line across here. So we're going to continue doing this on the map. And we'll do it up to here. And then we're going to go do this both horizontally and vertically. And we're going to do these basically based on the grids that we have on the outline of our cells here. And the reason why we use grids to do this is because if I want to know where a particular location is, it's very easy, given that I've put an overlaid grid on top of here, to figure out what grid a particular XY location is in. Okay, so let's take a look here and see what we can do with this. So I'm going to start to build an abstraction here. And the way I'm going to do it is we're going to look at each one of these cells that I've drawn right here. And we're going to ask, is this cell form a strongly connected component? This is an undirected graph. So the answer is, for instance, I'm going to get one node here. I'm going to get one node here. And I'm going to basically, each of these strongly connected components is going to become a node in an abstract graph, which represents my entire state space. So if I look up here, I have a node here. Now this is actually an interesting case right here. Inside this square, there are two strongly connected components, one on the left and one on the right. And the idea here is that I cannot actually get across between these components without leaving this. So we're going to call these sectors, and we're going to call these regions inside here. And since we cannot get between these regions without leaving this sector, we're going to mark them as separate strongly connected components. So we'll have another one right here. And then we can continue to do that. So we also would notice as I continue across the map, okay, so I'd get one here. These are fairly straightforward. In this area, I'll get one here. I get one here. But notice in the next component of the map, I'm going to get both one here and one here, because this part of the map is not strongly connected to this part of the map. And continuing here. And of course, I could continue to do this for the entire map, but I'm not going to do this all here. And so this gives us the strongly connected components. We're going to group them together, and those are going to give us states in an abstract graph, okay, which I've marked in blue here. And then the next thing that we're going to get is we're going to get edges in an abstract graph. And the edges are basically between groups or these states if they're reachable between each other. And so in particular, we would go and look at the border of each of these different regions. And as we look at the borders of these regions, we can ask whether states are reachable from one to the other. And if they are, well, there is a state that borders between here, then we're going to add edges in between them. So all of these regions here are connected to each other. Draw that a little bit more straight. This region, so if we look at this region right here, we can reach this region. We can also reach here. We can also reach here. And we can also reach there. So there are states inside here which will allow us to be connected there. We'll be connected here, here, and there. Similarly, this state will be connected here and will be connected there. But we notice that like states up here can only reach these neighboring states right here. And so the number of edges here is limited. Continuing this out a little bit, we can see, although there's an obstacle, we cannot go straight between these two states. So this is an important thing to understand. We can't go straight between here, but we can walk around this obstacle. And so we're really only marking connectivity. What I'm drawing here is not the actual paths we would take, but a representation of the connectivity. We'd say I can also reach here, I can reach here, I can reach here. All of these can reach each other. And these can all reach each other as well. And if I were to draw them, we would see that I could also reach down into here, can reach here and across there. Okay, so what we started to build here is we've started to build an abstract graph that is representing all the states in the state space. So what we see is that every state in the original map is represented by exactly one abstract state. And every abstract state, directly represents then, some set of states, which will eventually, every state will be represented by one abstract state in the map. And if we're able to do this, which we can over the entire map, then the question is, how can we use this for pathfinding? So what I'm going to do is I'm going to go through the entire process for doing pathfinding, given that we've built this type of abstraction. And let me say a little bit more. So there's lots of different representations that could be used for building an abstraction like this, and there's lots of trade-offs that can be done here. So for instance, we could choose, do I want to put this point? I could put it up here, I could put it over here, I could really put it anywhere here. This is going to affect some of our pathfinding process here, but it won't change the correctness results of what we're doing. So there's a lot of choices, there's a lot of different ways you can do this depending on the exact makeup of what you're doing. But one of the things we notice is if I think about this map, if this map is taking a lot of memory and a lot of overhead, then this abstraction is going to be very, very small in relationship to the entire map. So building a heuristic, and even trying to build, a limited heuristic, maybe, something like several differential heuristics, some Euclidean embedding, or even trying to think about using the using what we looked at in the last video, where we take the all pairs shortest path data and compress it into a compressed path database. That data is going to be very expensive, could be still very expensive to store relative to the size of this map. If we think about having this on a mobile device. The other thing is that many times in games, we have the maps change dynamically. And so if the map is going to change dynamically, if like I'm going to add new walls or things like this that are going to change the connectivity of the map, then I'm not going to necessarily going to be able to afford to do large amounts of pre-computation. There are some ways to handle this, to adapt something like compressed path databases to be something more akin to heuristics. But I'm not going to talk about this in this video. But the idea here is that these abstractions here are very locally computed, and they can be very locally updated. So they're going to be very effective in domains that are highly dynamic, and where the memory overhead of trying to do some computation is too large. And so, oh, actually, it looks like I missed an edge over here. We have another edge over there. There's some more edges. Okay. So how do we actually do pathfinding? So what does the pathfinding request look like? And I'm going to draw it a little bit farther down here. And I'm going to draw it in some open space so that we don't get bogged down here. But let's just suppose that this is my start, and over here is my goal. Okay. And so we're not going to worry about what happens over here. We'll figure out sort of what happens here, and then we'll extrapolate that out. So the idea is, if normally what would happen here is I would run an A* search, and we would basically be expected to expand all the states that are inside here, and then we would leak out of there and we would get to the goal. And so the number of states expanded would be the number of here plus here, unless we have some sort of other oracle information, either a heuristic or constraints or something else. But the idea here is that these are states in the original state space, and then we have states in an abstract state space. And so the first thing we need to do is what's called localization. And I need to figure out where is this state in the state space. And so I can do that first, of course, on this grid. Just by dividing by the grid size, I can figure out what grid cell I'm in here. And then when I'm inside the grid, if I'm in a grid cell like this one that has multiple regions inside it, I need to figure out additionally what region I am inside here. So this graph is basically, the nodes in here are stored by a sector and then the region number within that sector. Now we could think about, well, for every state, I'm going to store, which I know what sectors it's in, so I could store what region it's in. That would be a little bit expensive. And so we're thinking more about memory constrained domains here. What we could be doing instead actually is, if I'm at some location, I actually can just do a small search with inside here. Or if I'm over here, I could do a small search to figure out until I find this location, which is the center of the region here. So I can either use some search, or if I have the storage, I could use some pre-computation to be able to map this state onto, from the low-level map onto the abstract map that is much more sparse. And once I'm on this graph, then I'm able to now basically take any point. So that's, we'll go ahead and use this pink here. So I'd come over here and basically I can do a pathfinding request, which would give me a path to, actually, let me change this. It doesn't actually take me necessarily to that state, but it would take me to somewhere that is nearby that state. And similarly here, what we would be getting is we'd be getting a pathfinding request from a region center to a region center, but I actually have a start or a goal here. Okay, and so this path here is going to follow the region centers. The region centers are just basically going to be aligned here. I might as well draw some of these. So it would be like going from here to here, here to here, here to there. This one maybe should be a tiny bit over, but I'm trying to distinguish it between that state. And so what I can do here now is I actually can extract out this path. That gives me a path in the abstract state space. And given that abstract path, all I need to do is connect the goal to here, the start to there, and voila, I have an entire path through the state space. In this case, I'd want to go this way, but I'll have an entire path through the state space. And if we look at this state space here, if I think here, I'm going to have maybe 1, 2, 3, 4, 5, 6, 7, there's something like 6 or 7 when I count these here, nodes in this abstract graph in place of several hundred nodes that are in the actual low-level graph down here. So by abstracting this graph, I get a very, very sparse graph relative to the actual state space here. So if you think about maybe these are 16 by 16, you might have 256 states in here. I could get something like a 256 times reduction of my state space. And I'm just very simply going to come over here and get my path between my start and my goal. I connect the start and the goal, and I'm done. I have a path. And so this is the basic idea of abstraction and refinement, is that we can do this localization process to get onto the abstraction. Once we're on the abstraction, then I can do a pathfinding request in the abstraction, and then I simply connect the start and the goal, which in fact, if I'm doing localization, I'll already have found that connection. I'll have this entire path, and everything will look really good. And if we look overall at the work that's required to do this compared to something like A star, we can easily get 100 or even 1,000 times speed up, depending on the size of your state space and the size of the problems that you're following. But could very easily, 10 or 100 times speed up on very typical maps when we are trying to solve a variety of different problems. So this is something that can give us very, very fast paths. But what we're going to give up is we're going to give up optimality. Because in particular here, we're going towards a region center, we're going out here, and then we're going to go back to, or going in the other direction. We're going to connect things together there. And so there's a couple questions we could ask, but let me do this since, as I said, this deployed in an actual game. Let me go ahead and just show you a couple screenshots of what this looks like or this looked like when it's actually deployed in the game Dragon Age Origins. So there are actually maps on the Moving AI website where you can see different maps from this. But let's take a look at some maps here. So this is an example map. As I said, you'll find this on, you can find this exact map, but this is from the deployment of the game. And here we actually built 2 abstractions. One abstraction was at the red level, one abstraction was at the yellow level. And so from this, you can see when we did pathfinding, we'd actually do pathfinding at the yellow level and then pathfinding at the red level and then do pathfinding in the real world. And so this takes what is a very large map and makes it quite a bit smaller. And what's particularly interesting about this problem is that you notice this problem is basically a straight line. The area in the middle is basically a staircase that takes you up to the next level. And if you follow that out, you can go around in a circle and get back to the beginning. But there's a wall between those areas. You can look over the wall and you can basically click your mouse on the other side of the wall and say, be able to pathfind all the way around this map. And so having this abstraction allows us to be able to pathfind all the way across the map in just a single step. Or sorry, not a single step, but be able to do it very efficiently. On very large maps, so this is Ostagar, and here we have even larger abstraction. But in a map like this, again, we have 2 levels of abstraction. It allows us to do pathfinding from one level of a map to another level of the map. And here's another level on the map. This is from the human noble origin. Again, we can see that well, you can't necessarily see the underlying grid representation, but it's possible to see that presumably it's very small compared to what is actually going on in the entire map, and the abstraction, especially at the yellow level, is fairly small there. So that gives us a picture of how we're able to build that abstraction. And we will actually, what let's do is let's go ahead and look at a demo, if I can find my screen for that. Okay, so we're going to pull up a demo here and we can watch actually how this runs in practice. Okay, so here's a demo of a map. This is actually a map taken from Baldur's Gate. And on this particular map, we can see the yellow, which gives us the sectors on the map. And then within the yellow area, we see these sort of turquoise lines here. And the turquoise lines are between the different regions. So something to look at is, look at the different squares. I apologize, my mouse doesn't show up here, but you can find quite a few different squares on the map where there are 2 different regions within the same sector that are not reachable because they're different parts of the map, but the representation of the regions allows those to be represented independently. And so what we can do here is, there's a demo on the web that allows you to play around and look at different maps and other things like this. I'm just going to show a pathfinding request on top of here. So we're going to drag a pathfinding request from the top of the map to the bottom of the map. And if you remember seeing this before, this is a request that would require you to expand, a vast majority of the states in this state space. But what we're able to do here is, and I'm just manually stepping this here, we can see that the search is going outwards, and the yellow state is the one that's going to be expanded next. So we are still going to expand. We're going to go into a lot of local minima in the map. We're going to do a lot of work in expanding out different areas here. But actually, compared to the underlying grid, which is, got potentially hundreds of states, for a single abstract state, the cost of this search is very inexpensive. And eventually what's going to happen is we'll get down to the bottom and we'll get a path, which we can now see in blue here. Now, as I said a minute ago, the path here is not directly followable in the world. Particularly at the top of the path, we can see that it goes through an obstacle. And so what I want to talk about next is some of the things that we can do to actually follow these paths and to actually refine them into this refinement process. Because I said how we find this abstract path, but and we're guaranteed actually that the abstract path, we've guaranteed that each node represents a strongly connected region, and then each edge represents an exit basically from that sector and region to a different sector and a different region. So we really know that we can, this is the downward refinement property, says that any path in the abstract state space is guaranteed to be able to be converted into a path in the actual state space because of these strongly connected components that we're getting, that we're using to build the abstraction. And so we will be able to refine this, and the refinement actually gives us several nice properties. So let's go back to our slides here, and we will continue to look at how some of these things work. Okay, so what we're looking at here is we've talked about how we do the abstraction. This is up here. So this is the abstraction process. We find strongly connected components, which are each of these are strongly connected components. We add edges between the regions that we have from the strongly connected components. And then we can do a pathfinding by doing localization onto the abstraction, do a pathfinding request in the abstraction, but this actually isn't necessarily a walkable path directly in the world because, as I said, it could be going through an obstacle here. And so one thing that we could do is, to make this skinnier again. So one thing that we could do is we could just actually pre-compute. We could actually pre-compute for two nodes right here. We could say, well, here's the path between them, here's the path between them, here's the path between them, and we would actually store all the paths in here. And while you can do that, that's a little bit expensive. So whether you have memory to do that or not determines whether you want to do it at all. The other thing is maybe you could do that for some of the paths in the world. So for instance, some of the paths are heuristic, like the heuristic should just be followed to go along this path, where other ones would be quite a bit more difficult to do. And so we might want to think about that complexity. The other thing we might see is that there are states that have high reach. So a state like this is going to have higher reach than a state here. So the states with high reach might be the ones that are more important to store the paths, where the states with low reach, we're not going to need these paths nearly as often, so they wouldn't be as efficient to store in practice. Okay, so how we're going to do pathfinding. So we're going to let's talk about, and the reason I'm going to talk about this is actually because this has a big impact on path quality. And when we actually went to deploy something like this in the world, then path quality actually matters. And so let's start here. Well, I've got my, I do have this grid sitting here. So if we think about this, looking at a grid here and looking at a sort of an abstract way where I can draw it here. When I put an obstacle here, in fact, in a real game, there's many other considerations. So for instance, we might have somebody who's standing right here, and we may say that's an area that you want to avoid. And so even though by default, there might be a path that goes through here that you might want to follow in the world, that path might go through someone who's standing there, and in practice, we want to actually walk around them. Or there might be a spell that's being cast that we want to walk around here. So what are we going to do when I give you an abstract path? So an abstract path might look something like, I'm going to make my obstacle just go a little bit farther down here to make it more interesting. Okay, so my abstract path might look something like this in the world, and maybe it continues to here. And so all I have to do is I know basically the fact that there is an edge between two states. So I know there's an edge between here, says that I can do a search and I will actually find a path, which I'll draw in blue. So I can really just do if I'm thinking about a path that goes from here onto the abstraction, it's going to come across, and here is going to come off of the abstraction. So this is the start, this is the goal. Then when I go between here and here, I can actually just do an A* search. I could take into the account the costs of dynamic things, dynamic obstacles, dynamic costs in the world. And I could say, well, now I'm actually going to do a pathfinding request around here. And this is how I'm going to find, even though I could walk through this region right here, I might allow the A* to go around here because of the cost that exists there in the world. I'm going to walk around there. Then here, I'm going to just do a straight pathfinding request, and then I'm going to walk to there. And so I'm going to get this path that ideally, of course, if there's a region here, I'm going to see why there's a region. Maybe there'll be a fire there, or there's someone standing there. And so the reason why I'm walking around them is somewhat obvious, but I'm going to now get a path that looks somewhat reasonable in the world. But I still have some pieces here that are not particularly that are going to sort of look like these real straight line segments. I'm going to have these funny turns where maybe I just want to walk straight here. And so in practice then, what we're going to want to do is think about smoothing. And there are some techniques. We didn't get to talk about them at all in this class. And so if we were to extend the class another week, we're coming to the end here. But if I was to extend this class another week, one of the things I would probably talk about is any angle pathfinding, because that is something that there's, especially any angle on grids, there's been quite a bit of recent work on that has really opened up the possibilities of what you can do when planning on grids. But if we're doing pathfinding here, then what we might be able to just do is some post-processing. So I'll use a different color here again. Let's go and just use a darker blue. So what I might do is I might notice that, for instance, between here and here, we could cut that path off. And as we come around this corner here, we might realize that the goal is directly reachable. And so I could do some straight line smoothing there, and we would actually end up with a much better path in practice. And so that's something that we can do. And in fact, I can go back over to a video here and show, this is a video from early in the development of Dragon Age, where we can actually show the pathfinding here. Okay, so we're going to show the pathfinding request here. So this is the start state, and over here is going to be the goal state. And what you're going to see is that there's going to be some pieces that are planned. In fact, it's going to circle them as we go here that are being planned. We'll see the red line is the path being planned, and then they're being smoothed during the planning process. So right here, that part is very blocky, and that's being smoothed out. So by the time we get around this corner, and then we're going to look up here, and we see the path up there is a little bit blocky, and then it's going to get smoothed out. And by the time we get to the end of this path, even though our original path was a fairly, I'll just stop it here. Our original path is fairly blocky, in that we see a lot of line segments that have sharp angles on them. By just doing some local smoothing on them, again here. So here's the complete path as it's planned using the abstraction. We can see quite a few different angles, 45-degree angles and things like that. But as we continue this process, what we're going to see is that we get to a fairly smooth path at the end. So that's nice. That seems to do some of the things that we might want to handle or have to deal with. But there's some problems that can exist here. And so I want to go through some more things that are issues, again, that came out of actually trying to implement this in practice and come up with the best quality possible. And so here I'm going to show, let's look at it. Let's sort of ask, what are some of the bad things that can happen? And so let's do another example here. And what we want to think about is, well, let me show a couple of different examples, and then this will sort of work us through what are some of the issues that occur here. So for instance, here we could imagine just sort of a straight line where I'm going to start, let's say I start here. I'm going to get onto the abstraction, so I'm going to be following the abstraction across here. But what if my goal is over here? And what can happen here is basically, well, I'm going to walk along this abstraction, and then when I connect the goal together, I'm actually going to get to the end of my path, and I'm going to turn around and face the other direction. And this happens as a result of the abstraction, but it even happens, it really can happen in, if you're not using a planning algorithm that actually exists in the free space of the entire state space. So, you can have this problem where this could actually just be a grid cell. It doesn't even have to be an abstraction, because a grid cell is an abstraction. It could even be a polygon if we're pathfinding between polygon centers, where I could end up doing something like this. So this isn't necessarily a grid-based problem, but we can get some really bad things that happen here. And so let's take a look at this example where I'm going to put an obstacle in the middle of a grid. And we're going to think about pathfinding around this. So if I think about this, when I get my abstraction, I'm going to get something that looks about like this. And actually, we're going to make it even simpler than that. Sorry. So let's go a little bit simpler. We'll leave it as this. So if I think about this, what if I think about this problem here, and let me just draw a little bit of the abstraction in here. So what does the abstraction look like? It's going to look like this. And so if I'm thinking about the start and the goal right here, and let me draw those in a different color because we're going to do two different examples. Suppose that my start and my goal are right here. There's two different things that can happen here. So one thing is that I might walk to my abstraction center. I might then walk around here and then walk back to that location. And that doesn't look very good. And there's actually a fix for this, which is fairly simple, which says you should never actually walk to your region center when you're starting here. You should actually walk not to your region center, but actually just walk to the next one. So if I do this, and at the very end we do the opposite. You don't go to the very end location and then to your goal. You actually go to the second to the end location and then go to your goal. And so if I do that, what's going to happen here is I'm actually going to end up walking to there. I'm going to walk to there, and then I'm going to walk to there. And if I do some smoothing, I'm basically going to end up walking straight from my start to the goal. So this is just an example. When I have obstacles like this, I can get some cases that are not great cases where I look really dumb walking to my region center and then walking around in this direction. But by doing some local optimizations about where I path, I can end up with much better paths here, which I eventually can smooth out. The issue here, though, is that, or one of the issues here, though, is that I might end up actually walking around this way and so going around like that, when there was actually a really short path this way, I could actually walk a long ways this way. And that's because when I think about pathing from these region centers here, those two paths look the same, whether I go around this way or go around this way. So there's other, again, implementation enhancements we can do here. And so, for instance, one of the things that we did in Dragon Age is that we dynamically modified the map. So when I had this problem where I was going between here and here, and I wanted to path between some location here and some location here, what we can do is we could actually just dynamically move that region center over to exist right here, so that the representation of my world now looks like this. And when we do that and do a pathfinding request, then I'm going to go around the short side here, and I'll never tend to go around the long side. There's still some cases where something like that could happen in practice, but basically these are some things here where the fact that I've done abstraction is introducing some amount of error into my state space, and introducing that error basically causes the type of paths that I follow to look very different. Like if I think about this, it looks like these two paths are exactly the same, but I'm actually standing here versus here. And so the abstraction is removing some information, which is going to introduce some error, which is, related to the size of these sectors and something about the error on these edges here when I go around the world that might cause me to go in the wrong direction. So something we'd want to ask here then, so if you're building one of these in practice, you might want to be very aware of these types of issues, how they occur in practice, and the types of little optimizations you might want to do here to help make sure that you go around the right way, that you're smoothing out the paths that you get here, and other pieces like that. But we can ask the question, we can ask the question is, how bad can abstraction and refinement be? And this is in terms of suboptimality. And the question has to do with basically how we're representing our paths in the world. And as we're representing those paths, what is the error that's represented between the true path in the world and the shortest path? Okay, and so what we're going to do is we're going to draw a little problem here. And we can look at sort of what is the worst case. I'm going to use a slightly larger grid just to make this easier to draw. What is the worst case? So for instance, I might have an abstraction that says I go into this cell and I come out of this cell. And I can think about this, what are my distances? My distances are typically might just be like the straight line distances here between these points. So I might say like, I've got a point here and this is my abstraction. And the question is, what if I introduce some error on some particular edge? Then I want to think about, I might think that this is a very short path, but I might represent it as a very long path. And similarly, I might have something that I represent as a very long path, which is actually a very short path. So let's give some examples of this. So suppose here, let's just suppose that this is the entrance here. What I'm going to do is I'm going to say for this particular map, let's just suppose that in this cell here, the actual map looks something like this. And we're going to put an exit right here. So in my abstraction, it looks like I can just walk through here. But in practice, I have to walk up and down quite a bit to get through here. And the amount of abstraction I've done, so it could be as many cells as there are in this entire grid or sector. So the path, instead of looking at basically the width, could actually in practice be the number of cells here. So this would be like n versus n squared. And if we think about this happening not just at one level of abstraction, if I have multiple levels of abstraction, then I can get this multiplicative factor going all the way up, where a path can look much, much longer or could be much, much longer in the actual world than it is in the abstraction. And so if I do multiple levels of abstraction, I could actually get something like an exponential amount of suboptimality. Similarly speaking, I could have something like this. We'll just show another example where I can take something that is actually a very short path and make it look very long. And so again, what we're going to do here, so we're going to think about the some portion inside here. And the idea here is that if I have a map that I have an obstacle here. I'll just make my pen a little bit thicker. So I can draw my obstacle. So I'm going to have an obstacle that comes down here. It's going to force me, in fact, I'm going to have an obstacle that forces me to walk out of here. And then I'm going to have an obstacle that forces me to walk out of here. And an obstacle that forces me to walk out of here. So if right on the edge, if I ask where do I get my abstract regions here, what's going to happen is I'm going to get a region center here, one here, one here, one here. I'll get one here, 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 and here. And when I connect the edges together, I'm going to get something like this, where I'm going to say this is connected to here, this is connected to there, that's connected to there, it's connected to there, and here. So now when I think about starting here and trying to walk across here, because of the abstraction, in the abstract state space, I think that I have to go up and down here, where in practice, I actually only have to go straight across because I can just go in and out of here just barely. Okay, and it ends up that basically if you try to, well, there's some things you could do to try and compute this. And if I try and store enough information, I can actually fix cases like this, and I can even fix cases like this, right? I could just store the information, like what is the distance from here to here, and what is the distance from here to here. But once you start doing that, I can sort of be a malicious adversary, and I can continue to create examples where things work very badly. Now, the important thing is that actually when I go into a real game, real games don't tend to create structures like this because these are very tedious to do pathfinding through. And we also don't do real, structures like this. We tend to want to have open space where we can travel through them. And so although these worst cases could happen in games where we're doing abstraction, in practice, the cost of doing that is not necessarily going to be very huge in practice. And so, so we have this worst case inefficiency, but maybe in practice, we're not going to run into this. And so if we get to our, back to our ideas, let's just sort of give an overview of what are some of the things we've seen here. Okay, so if we want to summarize what's going on here, there's this idea of grouping states into strongly connected components, which allows us to form an abstract graph. Using this abstract graph, we can then do localization to get onto that abstract graph from some other location. When we get onto the abstract graph, we can do planning through it. When we do planning through it, we then do a refinement phase, where the refinement phase is this idea of doing individual pathfinding requests. So here we're looking at, I can actually, instead of trying to store that, I can actually do a search so that if there's dynamic obstacles or other things in the world, they'll allow me to search around that, which will allow me to do planning. In the case of pathfinding for video games, then we'll also be doing smoothing and other things on top of that to allow us to do this. And so this is the idea, as I said, of abstraction and refinement. We build an abstraction and then we refine these paths. So the downward refinement property we get because we have strongly connected components and the way the edges are connected between them, meaning that any abstract path has a low-level path that corresponds to it. And that also gives us these serializable sub goals where once I've gone to one particular point here, then I'm able to basically independently go from here to here and do each of these pieces of the path. Although I could do longer pieces together because they might actually give me better paths overall. So that's sort of a trade-off in cost there. Now I want to talk about two more things related to this. I'm going to do them very briefly. One of them I'll have a demo for. But the first thing we're going to see here is that this actually allows us to do our pathfinding much more quickly in practice and to allow the pathfinding computation to become incremental. So in a real game, players will often click many different locations in the game. They're going to be, they might make requests, they might change their minds, other things like that. And so if every time they make a request, we have to start planning from scratch again, then that's going to be a lot of work to redo every time we get a new request. And so one thing that we can do is that we can find an abstract path, but we actually are able to start moving along that. So we can refine a small portion of the abstract path. The rest of it, we leave it abstract. But if we do incremental refinement, then we can actually start moving before the pathfinding request is actually finished. And so if we go back to the example video that I was showing earlier in the class, I'll just bring this up again. We can see, if we look at this carefully, that it's going to do the same circling of the smoothing. But if we watch this, we'll actually see that, so here we are, there's a start and the goal, that we're going to start moving and the path itself, it won't be finished. So we're starting to move here in the world and we've moved along the first segment of this line, but we actually, that's going to get smoothed up there later, but we haven't actually finished walking along the path. So we haven't finished planning the path. In this case, we haven't finished refining the path. But even though we haven't finished refining it, we're able to still walk. And so we actually don't finish the entire path until somewhere around here. We can walk quite some distance before we do that. And in practice, there's things like level of detail where you say, I may not have a lot of time at this frame of the game. There's a lot of other things going on. So I don't want to spend the time right now. Maybe not just even because someone decided to change what they were, change what the request is, but maybe there's just 100 agents that are planning. And so each of them should only plan the next few steps instead of having all of them plan all of their steps all together. Or get their entire paths and wait for their entire paths before they start moving. So that's something that's very valuable. The second thing I want to talk about here is something that I mentioned in part of this here, but I didn't actually say too much about, which is this question here of what if we have costs in the world? And it ends up that if you're going to do pathfinding with costs and you actually want to do true pathfinding, it ends up that is a true shortest path. You're going to find you have to use something like Snell's law to determine how you actually follow angles through these regions of different costs. Now, we don't have to do that when we build an abstraction of the state space, and even grids are an abstraction, and we're sort of traveling through grid centers instead of trying to find true shortest paths. Again, there's some nice algorithms there we can talk about, or approximations that can be done here for weighted worlds, but we won't get to that in this class. But if I have weighted worlds like this, we might decide for a very, very complex or very rich world that we'd want to have a much richer representation of the world. And so you could imagine, for instance, that I might have a world. So let me just draw one here. So I can imagine I have a much more complex world. In this world, I'm going to have a lake here, and we'll have a stream that comes out of it, and maybe we have a stream coming into it. I'm going to put some trees around the lake, so there'll be trees on one side. And then we could imagine that people have carved a path out in the world. So there's this path that humans follow or are able to follow, and it cuts through the wood, and maybe there's a bridge, going over the stream or something like that. So there's something here. And, maybe it continues off in this direction as well. So if we think about a world like this is a very rich world. And if we try to do the basic type of abstraction that we've done here, then what happens is that we're not representing any of this information about the richness of the world. So we could ask this question, could we just sort of do the same thing and then do pathfinding with costs or something like that? And the answer is it's not going to work very well. So for instance, suppose I start here and then I want to go here. I'm going to tend to just go straight across the world, because in a world like this, actually, nothing is blocked. Everything is open. It's just a matter of costs. Like, I can walk through the water, I can swim across the lake, but it may be that it's much more expensive to do that than to follow this path. Or, maybe my horse is going to drown, but I can make it across. And so I may have some very strong preferences for the type of terrain that I want to be on. So we can use exactly the same idea that we've done of abstraction, where when we abstract a region, we may not want it only to be a strongly connected component, but we want it to be a strongly connected component of exactly the same terrain type. So that we'll abstract this water all as water, but inside here we want to say, well, this is water and this is trees, and they're connected, but there's some cost here to get between the water and the trees. It's going to be different to getting between the trees here and the trees here. And the path in particular will be its own abstraction. That'll be split, but its path in general will be its own abstraction, and it may be very inexpensive to plan along this path here. And therefore, we can have a world that is essentially entirely an open world with no obstacles, but very rich costs in it. And we can get people to actually follow paths here. So there is a demo of this. I will put it down in the links below, where you can draw these different types of terrain and you can do pathfinding through them. And if you look at the abstraction, you can toggle the abstraction on and off. You can see how the abstraction is built around different types of terrain. And then the other thing we can do is we can think about different types of creatures. So for instance, if we have a human, then they are perfectly happy to walk on the path, and that's where they would prefer to walk. But you could imagine a deer starting at the same start and the same goal location might much prefer to go and hop across the stream, walk through the forest, and then go that way. And I don't have to change my representation. I can just change my costs. And even in just changing my costs, I can get this differentiating of behaviors using exactly the same representation. So you could build like one representation for deer, one representation for horses, one representation for people, and they would all take slightly different paths. On the website, I think we have sheep. We have Jesus can walk on water, but we have all these, different representations of what costs may be. And so we can change those dynamically as much as we want, and we'll still be able to do pathfinding in the world. And in that particular demo, it's also designed so that we can do changes in the map, so that you can dynamically just come in and say, well, now I'm going to make the forest grow up here, and if the forest grows up here, then we'll just dynamically redo our abstraction locally, and we don't need to worry about having to rebuild everything, have to redo any paths or anything else like that. So this is also extensible into much richer environments. And the other thing that can go on here is that we may not want to work with grids at the lowest level. So I've shown this running with grids, but in some state spaces, we might have polygons that are actually representing what's going on here. And if we look at what is right now currently one of the popular polygon libraries for making polygons out of a state space, it's called Recast. What Recast actually does is it still actually uses grids here, but then each of these grids is broken into polygons. And so there's nothing special about doing abstraction on polygons versus grids. It's all just a question of, do I have strongly connected components? So saying that it's a polygon versus a grid at the low level really is inconsequential once I've said that I'm doing strongly connected components and adding edges. So what is the actual representation down here doesn't really matter. We'll use the same sort of technique and build the same sort of high-level graph. And so there is a paper on my webpage that describes this and how this is going in a game that is currently under development. And I don't know when that's going to be available, but this is something that's using these in a current game that's being developed today. So this concludes this idea of being able to do abstraction and refinement with a few enhancements here of looking at, what are some of the practical ways that we might get inefficiencies in our paths, or the way that abstraction can be representing things and get sort of lower quality paths, how we can fix some of those, how we can handle things like different cost terrain and even different representations of terrain underneath. And so that concludes this lecture on this abstraction and refinement. And there will be one more lecture, which will be basically a wrap-up lecture that looks at all of the things we've put together, and just say there's many other things. There's many other things we didn't get to talk about in the world. And actually, let me just say one more thing here to finish off. This idea of doing incremental refinement, we called PRA star, sorry, get my letters right here, P with just path refinement A star. And so that's the idea there. These abstractions, these went into the game of Dragon Age. There we called them minimum memory abstractions. These have also been called HPA star. So HPA star was a method which was doing hierarchical pathfinding version of A star. HPA star is also very popular. HPA star is actually the dual of this representation. So instead of having nodes represent regions and then edges represent the connections between them, it uses nodes to represent these connections, and then edges represent the ways that you can walk across one of these sectors. But it's very similar to HPA star, which was by Botia, Martin Mueller, and Jonathan Schaefer. And so PRA star was myself and Michael Burrow developed that, and we developed this several years before we then I then went and put it into the Dragon Age engine. Anyway, sorry, so a little bit extra there I wanted to throw in, give some acknowledgement to some of these ideas, and they continued to be used by other people in industry and variants for voxel worlds and other things like that. So that's a wrap for today, and we'll get our conclusion in the next video.